Hello and welcome back to the Astro Imaging channel. This week's session is on designing and building a low-cost dew heater system. And our presenter is Steve Sagarian, but as always, I do want to show off our image of the week. This one came welcome back to the Astro Imaging channel. This week's session is on designing and building a low-cost dew. Is that me or is that someone else? I think that might have been someone else, yeah. But yeah, so let me show off the image of the week. It's going to happen every time, I'm sure. This week's image of the week goes to Felix Ecker. IC434, the Horsehead Nebula and the Flame Nebula together in a nice kind of panoramic style. Taken from the Alps of Austria, two-panel mosaic with a Raza, the Celestron 11-inch astrograph, and an Attic 460 EXM camera. Excuse me. Interestingly enough, he took these with normal, non-high-speed narrowband filters, and we've had that discussion a few times before. Can you use normal narrowband filters with such a fast astrograph? And apparently the answer is yes, and you can get good results as well. But hey, when you have a chance, go on our website. You can check it out. You can leave comments and basically submit your own images for image of the week. So let me take my screen back here, and again, hopefully you're watching us from our website where you can get access to chat, log right in and ask your questions, and I will basically call them out to Steve. And this is going to be one of those where you're probably going to have a lot of questions. There are a lot of times where the standard off-the-shelf dew heater isn't going to do for you what you want. So this might be one of those times you're going to have to get creative, or maybe Steve's going to get creative for us. But Steve, I see you right there. I'm going to basically hand it right over to you now.
Okay. Let's see. Screen share. Full screen. Can you see me?
I can see. I see your full screen. Yes, I see me, but yes.
Perfect.
There we go.
Okay, let's get going here. Okay, so the title of this presentation is Dew Heater Design, or What I Learned on the Internet. This project kind of came out of my desire to try to run my 10-inch SCT remotely in my backyard all winter long. And up to this year, I did not own a dew heater, and so I started doing some research in them, and this is the result of that effort. So the presentation outline, I'll talk a little bit about the theory about dew heaters themselves and power, and then we'll list the steps to build the controller portion of a dew heater using inexpensive LED dimmers. Then we'll talk about kind of the theory of the design of the heater element itself, how to do that safely. And then we'll go through the steps of actually making a dew heater. I'll show you a bunch of pictures from what I've been doing. And then lastly, we'll talk about the battery requirements for a dark site now that you've got all these additional heating elements. I made a few assumptions about you guys. That you can solder a few wires together, or that you know somebody in your club who can help you with that. There are a few connectors that will require soldering. And then a comment, this presentation would make a great club project. So if you're trying to think of something to do with your club, this would be a great way to do that. You could share your expertise in what you've learned tonight, and also share extraneous costs, like your shipping costs if you're buying components and stuff. So let's get into it. One other thing, I guess I gave Adam a spreadsheet so you guys could play along at home.
Maybe I'll interrupt you there. If you're on our website, just look directly below the video, and there's a link to it right there.
Perfect. So go ahead and download that spreadsheet. It's very simple, and the various parts of it I've got labeled will cover some of the areas as we go through the design. Part B is probably the meat of the whole thing, talking about how to properly size the nichrome wire that you're going to use for the heater element and how to do that safely. And then part C is pretty simple as well. It's just summing up all the battery currents that you're going to be using for all of the devices you'll be taking to the field. Here's a picture of that spreadsheet, just a kind of quick overview of it. The let's see, can you see that little red thingy? Anybody, Adam?
Yes, we can.
Okay, all right, great. So the areas in blue are areas are things that you can enter. So for example, this MSPF, this is really a critical part of the whole design philosophy, and that is the maximum safe power factor. We'll talk about that more in detail later, but you can change this. So for various reasons, you might want to change it to be more aggressive in your heating, or I have it set kind of a very mild heat, just for my own purposes. I've set it at this value. If your system is 12 volts, you can set this. The nichrome wire per resistance per foot, depending on how many turns of wire you end up using, you might want to go to a higher resistance per foot. And I'll show you, if you play with this, this is actually a pull down. Part A, again, is for the controller. Part B is for the heater elements, and then part C is for the battery. And you can play around with this as much as you like. We'll talk about it a little bit more later. So why not just buy a heater element or a heater system? And for many people, that's a perfectly acceptable solution. They don't have time to fool with this stuff. I'm an engineer and I like tinkering around with this stuff, so for me it was something I enjoyed doing. Because primarily it's very simple, easy, and expensive to build. You can save a lot of money for other things. Certainly I'm sure everybody can think of something they would, if they had $200 or $300, they would spend to improve their astro imaging. To save from swapping heater elements between scopes. So if you have 3 scopes or 4 scopes and you only have 3 elements, you could make additional heating elements or heater systems and put one on each of them because they're so inexpensive. And even if you have a controller, you can make more heater elements. So how does dew and frost form? Well, condensation is the basic transformation of a substance from a gas to a liquid. All air contains water of some degree. And if that air cools past the dew point, condensation will occur. So this is one of my favorite images of condensation. This one is not. You can see from this picture that I think the thing that's interesting about this picture is that the heat from the camera is actually transmitting down through the base of onto the corrector plate, and you can see there's a slight area that has actually been frost-free. This is kind of scary. The sky acts to absorb. It acts like a heat sink, absorbing heat in something called radiative transfer. So anything that's pointed towards the sky will actually lose heat, and if conditions are right, will experience condensation. I think we've all, well, with the exception of people in Utah and Arizona, have experienced this. You can slow this process down a little bit by using a dew shield. So the dew shield will actually limit the amount of sky that your lens sees, thus sort of retarding that process, but it won't slow it down. So having a dew shield will slow it down, but it won't stop it completely. And that's where our lowly dew heater comes to the rescue. This is a kind of a high-level block diagram of what a heater system looks like, or is composed of. On the left here, you have your power supply. This could be your 12-volt battery from your dark sky or dark site. It could also be an AC to DC converter if you have a backyard observatory. The controller here acts to moderate the power delivered to the heating elements. So here are heating elements over here. And the heating elements convert electrical power to heat. The controller moderates the power delivered to the heating elements using a technique called pulse width modulation, or PWM. You may have heard of that term. The percent of on time is called the duty cycle. So these waveforms over here represent a PWM. This peak up here is the on period, and then down here is the off period. So the controller, excuse me, turns on and then turns off the voltage elements at a specific rate. And this is called the frequency. I'm sure most of you have heard of all of this before. In this diagram, you can see that this particular waveform, the duty cycle is very small. It's roughly 15% of this whole period. So the light bulb is kind of showing that it's kind of dim. Here, the duty cycle is a little bit more, and you can see the light bulb is on a little bit brighter. And then here you can see that the duty cycle is almost completely on, maybe, I don't know, 10% or so. And the light bulb is the brightest part. Now I'll have a demonstration of this later on, so we'll see that in action. And so here is your typical dew heater system. This is the one I actually built for this project. It has these adjustment knobs for adjusting the PWM output of the voltage. There are LED indicators indicating how strongly the control is on, and then there are ports here. These are typically called channels from a lot of the sales literature. I call them ports or channels, but basically each heater element will plug, or a heater element will plug into each one of these ports depending on how many heater elements you have in your system or on your telescope. Over here is the heater element itself. You can see it's a kind of a pad. Inside this pad, there's a coil of nichrome wire that heats up, and then that connects to this cable, which connects to this port. The cable here is meant to go to your battery. I've got these Anderson power pole connectors here. This could also be your standard cigarette lighter adapter connector if that's what you choose to use in your design. So this is the whole point of this project is you can use these LED dimmer modules. They do exactly what I talked about with the PWM control. We use one dimmer per channel, one output. And so you can use as many of these as you desire for your overall design. Now the eBay price of these things is $1.96 per unit. So this thing, the circuit board inside of it, the connectors, the housing, $1.96 shipped to your house. And so that kind of leads me into this rant. Here is a picture of that controller. These are called Phoenix connectors, these little green connectors. They're standard in the industry for high current, low voltage connections. This is the female part of it, and the male part of it is actually a part of the printed circuit board that's inside here. I can buy this whole thing for $1.96 from China, have it shipped to me for free. If I go to the American website DigiKey, which is a place where a lot of design engineers buy their components, I can only buy the connector, just this one connector, for $3.68. So I don't understand how they can do that, but I'm very happy to buy these and use them in my design. And because they're so cheap, I decided not to design my own when I was going about this. I said, I cannot do it as cheaply as I can buy it. So this is one of those buy it over design it decisions that I had to make. Now on this other side of that, that was my rant. So now I'll rave about these things. These LED dimmers are really nice. They're very simple. I reverse engineered them and looked at the components that are inside of them. The components will support a very high current needed for the dew heaters. I tested them up to 5 amps and they worked fantastically. They didn't overheat. They worked great. And the only reason I didn't go higher in my testing was that I didn't have half an ohm 50-watt heater test resistor to do that. So I'm pretty happy with these things. I recommend them for this project. So here's a 4-channel dew heater element or dew heater system in kind of a abstract form. So I'm showing you these dimmers, and here's a kind of a poor man's schematic. You can see the 12 volts here from your battery or from your power supply, and it's hooked up in parallel to each one of these. So this is how you would hook these up. The outputs, you can see up here, they actually have a legend, so you can kind of use this as your guide. The output are these 2 terminals, and this goes to your RCA jack and your LED indicator. And so you'd have one unique set of components for each output. So let's go ahead and let's build our controller. So the very first thing you got to do is take the good component out of that housing and take it apart. And that's what I've shown here. We're going to use our own housing, so you have to cut the holes for it. I had to cut some holes for the adjustment pots for 4 of the channels for the RC output ports. I also have indicator holes here for my indicator for my LEDs. And then I guess I don't show here, but I think it's I guess it should have been on this side. There's a hole for your power cable. Now on the bottom side of this housing, I've drilled some holes and I've mounted these screws. These are actually black nylon screws with some black nylon nuts to mount the printed circuit board. And here you see them mounted inside the housing. So these are the printed circuit boards that I took out of the original LED dimmer modules. I've mounted them, and I've left space up here for the female connector to plug into each one of these individually. And of course, you can see the adjustment pots sort of kind of hanging down here for right now. Okay, so these are the RCA jacks, and I've shown kind of them in the component exploded diagram here. This is the RCA jack itself, and it usually comes with this. Well, it does come with this return ring. And what I've done here is I've soldered a wire to it, and then I've heat shrinked the wire. And then I've done the same thing from this guy here. You can see there's a red wire, and I've heat shrink that. So this is you have to make 4 of these if you're making a 4-channel dew controller. I've just shown this one. And now I'm showing kind of the exploded diagram of the LED indicator, how it's wired up. In part A of the spreadsheet, if you're going to use something other than 12 volts, or if you're going to use an LED that has what's called a forward voltage, forward on voltage, you can enter those values into the spreadsheet. Let me bring that up real quick just to. Okay, so most LEDs have a forward voltage drop of 2 to 3.5 volts. So I've used 2.1 volts here just because that's, I think, what the data sheet said from my LEDs. And you typically want about 20 milliamps. This is 0.02 amps of current going through them to get the maximum brightness. And so using this voltage drop and this current through the LEDs and then this system voltage, it turns out we need a resistor of roughly 500 ohms, 49. Now you're not going to find 495 ohms exactly on DigiKey or on any of the other websites. So you can just roughly play, kind of get a ballpark number. So I think I ended up using like 512 ohms, which is something I probably had in my my kit here in my little lab.
Steve?
Yes, sir.
Zach is asking how important it is to how important is ground isolation or using filters in practice when using peripherals like a dew heater?
I guess I would not worry about it. I think most of the I didn't see very much noise on these. I could be wrong about that. He's suggesting we put some sort of filter between the dew heater element and the power supply, or between the dew heater.
I think that's what he's asking, and I know, like, I've heard people say that dew heaters can cause interference, and I'll be honest, I've never seen it myself, and I think that, or not being an engineer and not really understanding a lot of it, when I've asked people how to deal with it, they say, well, put a large capacitor on it. And what's a large capacitor? Well, a 12-volt battery, I think, is a large capacitor. So it might be something that we kind of over exaggerate the importance of. And Jeff Voigt is saying it's low voltage, so it shouldn't be an issue if you're worried about getting shocked. I don't know if he's worried about getting shocked or introducing some sort of noise into the system, particularly when using like a CCD, but I was speaking more to the latter than any sort of getting shocked, which
sure.
I don't.
So what I would suggest is on the 12-volt power line, putting about a 25-volt, like a 1 or a 10 microfarad capacitor across those lines. That will definitely filter out most of the noise coming from the from the heater element itself. So I would probably recommend that when you're building this thing. So let me kind of scroll back to. So right here in this diagram, I would probably buy a leaded 12-volt. Sorry, not 12-volt. Maybe a 25. Well, let me back up. If you're using a 48, well, you wouldn't use a 48 volts. So let's just stick to 12 volts. I would probably put a 25-volt 0.1 or 1 or even a 10 microfarad capacitor across these two lines. If it's a polarized capacitor, make sure you put the plus lead on the 12-volt side and the ground side on the ground side, the negative side on the ground side. And that'll cover most of your noise from these things, I think. You could also gang a couple of them. You could put a 0.1 and a 1 microfarad capacitor, and even a third, like a 10 microfarad capacitor. So at the end of the presentation, I've left my email address and my Cloudy Nights ID, so people can also send me questions if I don't answer quite what they're looking for here. I can try and recover it, give them a good answer later on. Is that good enough right now?
Yeah, I think you answered his question.
Okay, all right, great. So here's the LED indicator, and you need to wire it up in exactly the way I've exploded it here. So the red wire to the resistor, to the, if you notice that these LEDs have a lot, and I know a lot of you guys are probably engineers and you know this stuff. Some of you don't, but these LEDs have the longer lead, have actually two leads, one's longer. And so the resistor has to go to this lead, and then the black wire has to go to the shorter lead. And then of course, all this gets wrapped up with some heat shrink tubing to protect everybody, from shorting. So here's a picture of that, and I've got it on 12 volts here to test it. Excuse me. The power cable, again, is typically goes to your battery. And I've mentioned before, I use these Anderson power pole connectors. I like them. They're rated for 15 amps, I think, and you can kind of mate them together so they don't fall, they don't get twisted around. You can match them up to the power supply, and they're really easy to use. And they're also have a certain amount of tension strain that won't pull them apart, so they will stay together if they get tugged for a certain tension, I guess. The cigarette lighter adapter, I've never really liked these, but a lot of people still use them. This is a picture from one on eBay that has a switch in it, so you could actually turn the power on completely from this point, a fuse, and a little LED light, so you could actually see when you've turned the whole thing on. That's one thing my system does not have. When you go to buy these on eBay, make sure you read the description carefully, because some of them will have skimped and they won't have the fuse in it, or they might not have the LED in it, but they'll have the switch. You just got to read the description of what you're buying and make sure you get what you want. Here's a picture of the Anderson power pole connectors. These little silver crimps go over the stripped wire, and then you just crimp them down, and then you basically mate the housing on over top of it, or I guess you really insert it into the back of this hole here. Would be a better way to describe that. And then here's my cable. Here's a picture of the harness that I'm making. So these are the individual Phoenix connectors that I talked about earlier. You can see that I started to wire up the power bus side of this thing, and this is where you put those caps, by the way, if you were going to. So you put a cap on the red side, between this red and black wire, and you only need one for the whole gang of connectors. And then here's the final assembled controller. You can see that the PCBs are all mounted. The RCA connectors are in the holes, and they've been routed to their ports on the connector here. The pots have been placed inside the top, and they've been bolted in place. And then the LEDs are sort of just floating here. I'm getting ready to close it up, and I'll put them in these little LED holders here, 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 here. And so that's it with the controller. And now I'm gonna switch screens real quick. What we're looking at here is this is Google Slides. I'm gonna go back over to this is Microsoft PowerPoint Viewer. I don't have PowerPoint on this particular computer, and I'm going to show you. So here's the testing of the 4-channel controller. You can see the lights turning on. They go from off basically to full on. And let's see. So you can see this one channel here I've got actually hooked up to an oscilloscope, and we'll see the PWM that we talked about earlier. So here's a picture of the here's an oscilloscope image of the output of this one channel, and you can see that the duty cycle is almost completely on. It's full on. The average power is basically the current going through it times the voltage. And as I turn this on, and as I adjust this knob, you'll see it go down in average power and then back up in average power. So you can see there's the PWM that we all want for. And right about, there, you're really low power. You can basically turn that off, and then you go back up to full power. Okay, so that is the, switch back over to the Google. There we go. So we're back on Google. So let's talk about heater elements now.
Steve, I have a question.
Yes, sir.
What are the in the RCA connector? You had a shield or a wire ring on it. Where did that wire go in the box?
Okay, let me show you. So back up to my super duper schematic. So here's your RCA connector. And then remember, the red wire is the center wire from the RCA connector. This black wire is that ring wire. Do you follow that? So this goes to the negative side of the output, and the red wire, the center wire, goes to the plus side of the output. So let me put a picture of it. Yeah. So this is the red wire, and this is the black wire. This actually goes over this nut comes off, and then this ring goes over.
Okay, I made a mistake. There's a shadow next to that red wire. I thought that was an extra wire over there. I'm sorry.
Oh. Let's see. You talking about back here?
No. Go back to the connector.
Okay.
Yeah, right next to the red, right here. It looks like the black wire's over there, and the ring looked like an extra shield cable. That's where I got confused.
Okay, this is just some heat shrink tubing I've left out
Got it.
to show that. Okay. All right. Let's get back to the heater elements. These are typically called heater pads on some of the sales literature of some of the websites that sell heater systems, do heater systems. These two images are basically the same circuit. The one on the left is delivering a lot of power in a very short period of time, and the one on the right is delivering a small amount of power over the same time period. The one on the left you do not want touching your telescope. Before we talk about do heater elements, I want to talk a little bit about another technique for making these elements, and that is this resistor ladder wire arrangement. Many of you have seen this, maybe some of you have done this. I really don't recommend you doing this. It does work, and it is if you have a lot of resistors and the time to solder these. So let me show you another picture of it. So the idea is you run these two rails of wire, and then you solder these resistors every some distance apart, and then you trim them up. And it does have the same effect as a nichrome wire. The bad thing I don't like about it is you can see right there, there's that little sharp point it's gonna stab you in the finger in the middle of the night when you're trying to adjust this thing. Or it could possibly, worst case, it could short. This could be the 12-volt rail, and it could actually short or scratch your tube and short the 12-volt line to your OTA, which would be not a happy situation. So I don't recommend you using this. I think the approach that I've learned from the internet using the nichrome wire is safe and a much better approach. And so don't do this. Okay. Our heater elements will be made of nichrome wire. The length of this wire is determined. It will determine the total resistance of the element that we're trying to build. And we're going to use part B of the spreadsheet to calculate the length of the wire based on the resistance we need for the power that we're trying to deliver to the unit, to the heater element. The length is based on the size of the optical element. So what I mean by that is, I think I have a picture of it shortly. Typically, you're going to wrap your heater pad around the optical element that you're trying to protect. The length of that circumference will determine how much power you're delivering to that element. And I'll show you that shortly. So the length is based on the size of the optical element. The total power delivered is determined by what I call the maximum safe power factor. And again, I'll talk about that really quickly here. And the resistance is determined by using whatever the power factor is we determined, or the power that we determined will determine the resistance of the wire that we need. Based on, now the spreadsheet is based on 12-volt system, but you can also enter whatever voltage you're using. I know that some of the, I think astrophysics uses 48-volt systems, so you may not have a 12-volt battery. I'm not sure how you guys operate those things. Okay, so here's an example. This is your standard poor man's telescope for astro imaging. And I've just sort of whimsically picked out some circumferences here. So this OTA has a 32-inch circumference. This is 19 inches, and this is 13 inches. And there's, of course, three heater elements for our system here. Because this is 32 inches, this linear length, the power that I'm going to be using is 32 inches times my max power factor, max safety power factor, which I've chosen to be 0.25 watts per linear inch. So for the 32 element, I want to deliver 8 watts of power to that lens. For the 19 inch, it's the same principle. I want 4 watts. For the 13 inch, I want 3 watts. And you can play with the the spreadsheet and plug in whatever numbers you need for the, now the OTA dimensions are in inches. So if you have your primary, if you have a 128 millimeter scope, that's 5 inches, plug in 5 inches for your diameter. And that'll tell you how many, you know, how long the heater element is, how many watts it's going to be using, and how many ohms we need to get that power. As you can see by playing around with it. Okay. I want to talk a little bit about max safe power factor. In the literature that I read online, most of the places used 0.75 watts per linear foot. But I tried that, and I found that it was, in some cases, like on full power, the heating pad got extremely hot. It wasn't that I couldn't touch it or hold it, but I just felt I didn't want that much energy being delivered to my OTA paint job. I just felt like at some point it might ruin the paint, or it might do something to the you know, the telescope itself. So I've been experimenting with 0.5 watts and 0.25 watts. And for what I use here, I use 0.25 watts, and I find that is it works well. I get enough. The heating elements get hot, but they don't get uncomfortably hot. And I think in an environment like in Chicago, where you might be outside in the middle of winter, sub-zero, I think that's plenty of energy. But I'm also saying that you can experiment with these and try what you like. I think the 0.75 watts is probably still safe for you to use. I don't think you'll damage your telescope or your paint job or anything using that high power. But for me, I felt more safer recommending this 0.25 watts. Okay, so this slide really kind of summarizes what I've been talking about. Let me just skip this one. I want to talk a little bit about nichrome wire. Now, this table I got from, well, I summarized it from an online website called jacobsonline.biz. This guy sells nichrome wire. And I found a lot of the discussions on cloudy nights kind of pointing to this website. So I summarized it here in terms of the gauge of wire will determine how many ohms per foot you get. And it just turns out that I bought my nichrome wire from McMaster, and it turned out to be this 28 gauge 4 ohm wire. And so I used that. And I really like that value because you can see the diameter of the wire it goes from fairly big to really, this is like 3 mils, not much thicker than some of the garbage bags we use. So I think that this is a good value to use. You probably won't break that wire over, you know, a couple of years of experience. This wire, I would be fearful it would be prone to break. The other thing is that you would have really short heater elements with this wire. So let's move on. Okay, so here are all the components I need for my heater pad. I've got this RCA cable with a RCA male plug already attached to it. I've used my calculations for my lens element to cut some nichrome wire, and then I've taken that nichrome wire and I've sheathed it inside this heat shrink tubing. So I think this was roughly about 6 feet of nichrome wire, and I just cut 2-foot sections of this and then slipped it over the nichrome wire until I had it all fully covered up, with the exception of just these 2 leads here. This is a single-sided adhesive paper and a couple of heat shrink tubing for these crimps. You can't actually solder nichrome wire to anything, so you actually have to crimp it with some crimps to make a joint, and I'll show you that shortly. Here's some RCA plugs. These two over here are the kind you need to basically thread the cable through and then solder to the internal tabs. You pull this plastic housing back and solder them. This is a solderless one, so this is kind of useful for people who don't want to solder. You just strip the wires, plug them into these holes here, and push down and insert it a little bit further, and then when you release this little button here, it locks it in place and you don't have to solder it. So those are convenient for people who don't like to solder. Here's a picture of the heat shrink tubing. You cut the wire to length based on the resistance you need, and then you cover it with this heat shrink tubing. So that kind of makes it insulated, a little safer. So we excuse me. So we start with this adhesive back paper, and I've drawn this dotted line. Here's where I'm going to fold the paper. I'm actually going to pull the release liner back, and we're going to lay the nichrome wire in loops along this section here, and I'll show you that. So I pulled the release liner back, and I've drawn a line. This area outside here is like a keep out area. You don't want to put anything in here. We're going to run our nichrome wire back and forth in this area. The adhesive will keep it in place while we do the looping, so it makes it easy to do that. So you can see here I've got my first loop started. I'm going to gently loop this back and go back and forth and back and forth. And I want to end up with the same lead, or my end lead along the same line, so that I can crimp these. So you can see here's the completed coil of nichrome wire. I'm running it back and forth, back and forth. I finish up here. This last loop I had to go halfway just to make sure that I got this even with that one. And now I've twisted the wires. You've got my red wire going to one end. It doesn't really matter which way you hook this up. This is, the current going through this wire will heat it in either direction. But I've twisted these wires securely, and now I'm going to crimp them. So I've crimped them. You see these are your standard crimps you can buy at an automotive store. You might even have some in your garage. They're made for making physical connections to wires without actually soldering. And now I've pulled the last part of the release liner off. This thing is called a release liner. And now I'm going to fold this back over, give me a nice little ravioli of heating coil. So you can see that I've folded it over. I'm covered the entire coil with the paper, and I've sealed it along the edges of my keep out area. Everything is nice and tight and tidy. And now I'm going to use my favorite duct tape to seal it a little bit further. I've laid the duct tape down here in 2 strips, and I folded it back over on top of the heater element. And now I'm going to put one last piece of duct tape here, and voila, I have a heater element that is going to deliver the right safe amount of power to the optical element that I'm trying to heat. And I've gently formed it into a circle here, so you can kind of visualize what it would look like on your eyepiece or on your finder scope. And just as a side, I also will make a label. I have a label maker, and I'll put the amount of current that this element draws. You can see I put it here, just as a kind of a thing. That way I can sort of, when I'm in the field, remember how many amps this will actually draw if I need to do that. So then we're going to test this thing, and the way you test it is you plug it into the controller, you turn up the power, and you just let it run for an hour and see how warm it gets. If you've done it right, this thing will get hot, but it won't get too hot that you can't touch it. You can put it at half the adjustment level, and it should feel warm and comfortable to hold onto. And once you've done that, you got it made. You've got your first heater element. Okay, and then so here's my little humble system. I have a 5-inch Skywatcher with a Canon T3i that I've modded myself. Here's my 5-inch heater element. Here's my 2-inch heater element. And then here's my controller. This wire goes down to I have a AC to DC 12-volt power supply that can deliver up to 40 amps. So I'm set for power here. And you can see that these two elements are being powered, and it's good to go. Okay, so we're done. We've built a DO heater controller, 4-channel if you follow these instructions, or 2-channel if you want to grab and go, or whatever size you want to make. Because they're so inexpensive, you can do whatever you like in terms of the number of ports you want. But this does affect your dark site battery sizing. So you may need a bigger battery, and that's where part C of the spreadsheet comes in. All of the currents that you put into part B, all the elements like the primary objective, the finder scope, or your guide scope, all those currents are now summed down in part C, so you can enter the additional things that you take to the field. So for example, your mount will draw some current from your battery. Your cameras, especially if they're using the Peltier cooler units, those things typically draw a lot of current, amps rather than tenths of amps. Your guide camera, anything else you're hooking your battery to, you can enter those fields in this part C, and you can see the total current you're going to need for the number of hours you decided you're going to be out to the field. So you can see off to the left on the spreadsheet, it says observing time, and I think I left the default as 6 hours. Sometimes that's a little bit optimistic for me, but I know people who will go out and stay all night. And I've also derated the battery to by about 20%. You could change that if you don't feel that that's typical for you. That just means that you're not going to draw the entire amp hour capacity of that battery. You're only going to draw roughly 80% of that battery over the period of time you're on the field. Okay, on to the next page. This is just a real quick summary of the materials. It's not a full list. I need to update this. I think the most expensive thing on the whole list is the nichrome wire, and that might be $10 for like a 300-foot spool. It's really cheap on McMaster. That other place sells it inexpensively as well. Let's see what else. I think that's it. So a little bit about me. My name is Steve Sigurian. I'm an embedded hardware and firmware engineer. I have had a lifelong interest in astronomy. I'm also involved with the OnStep project. There's a gentleman, Howard Dutton, who's designed a mount controller, which is a phenomenal software, and I helped him in designing this hardware board. This is a shield board for Arduino of the AT-Mega 2560. This is my Cloudy Nights ID, and this is my email address. You can reach me if you have any questions about the presentation, and I'll be happy to help you with your design if you decide to do one of these. And that is it. How do I turn this over back to you?
Awesome. Thank you, Steve. First thing I've got to say, I love your duct tape. My daughter would love your duct tape. She loves penguins.
Well, thank you.
One of the questions that popped up was, do you recommend using a separate battery for your DO heater when you're running it with other gear?
I don't think so. I think as long as you have like a deep cycle marine battery that you're taking to the field, and it will meet the current requirements that are like kind of called out in part C of that spreadsheet, I don't see a reason to carry yet another battery out to the field.
Okay. Yeah, I'll say this. I do use a separate battery for my dew heater, and I did it because at one point I was getting interference on my CCD camera, and excuse me, even though I'm using the separate battery, I still on occasion get the interference on my CCD camera. So I'm fixing a problem that, well, I should say, I'm not fixing the problem, but I'm still doing it that way. And I think it, like I said earlier, I think it might be one of those things where it's kind of overkill. We may not really need to do it, but I know a lot of people say it. Even astrophysics, they say, keep your mount on an independent battery. And with my mount, well, actually, I run my mount off AC, but when I'm in my observatory. But I think it's one of those things where try it. If it causes a problem, then switch it. But if it doesn't cause a problem, then you're probably good to go. And as always, it's good to keep the same system running basically all the time. So keep the wiring the same, use the same batteries if you're in an observatory, and if you go elsewhere, try and keep as much of it the same as possible so that if you are going to have issues, you know which issues you're going to have, and you get familiar with your system. And was there another one in here? I think most of the other ones, what gauge wire, there was a spreadsheet in there that you should, Jerry, that you should go in and see, because it's going to depend on a few things. Oh, what gauge wire in regards to, yeah, what gauge wire in regards to the 12-volt wire that's coming from the battery. And I use that same website that Jeff posted, wiresizecalculator.net. It basically, you just go by the expected draw and you give it some overkill. Go a little bit bigger and then you're fine.
That's exactly right.
But I think that's basically it. I do hope. I think you probably, Bob. Did you find the link yet? I'm guessing you found the link because we posted a link in chat to it. But for that spreadsheet, which will be handy if you're trying to do this yourself. But yeah, excuse me. Thanks again, Steve. Steve's suffering from, I think, the same cough I have, so that's why I heard him coughing, and I know exactly what he's feeling like because I was pausing my mic, coughing up a storm while he was talking. But oh my goodness. But again, thanks. I'm sorry. I digress. I'm sorry. Thank you all for coming. We do not have a presentation yet for next week scheduled. I will try and come up with something. We may do something like an open session where we can help you guys troubleshoot some stuff. I will post it midweek unless someone happens to email me and says, oh yeah, that presentation I was talking about, or I have a great idea for a presentation, or whatever it may be. But yeah, give me an email if you guys have a good idea for a presentation, or if you're thinking you may like to present. But for now, again, I just want to thank Steve one more time, and to all of you guys, good night. See you next week.